Welcome back to the deep dive. Our mission today is pretty laser focused. We want to understand the foundational math toolkit, the one that underpins, well, pretty much every single modern machine learning model. We're doing a deep dive into the source material you shared with us, showing you the shortcuts to really getting concepts like linear algebra, geometry, and optimization.
And if you're listening and immediately feeling that wave of anxiety, you are not alone. One of the sources we looked at today just captures that feeling perfectly. It says, math is linked in the popular mind with phobia and anxiety. You'd think we're discussing spiders.
That anxiety is definitely real. But the good news is the math isn't there to make things complicated. It's there to make them precise.
Precisely. That's the perfect word for it. Mathematics gives you the structure you need to formalize concepts that are otherwise just intuitive. It's the language that lets you translate an idea like finding the best fit into a robust working algorithm. Without that language, those ideas just stay vague, unusable.
So our mission today is to distill those core concepts, the vectors, the matrix stuff, the calculus, and show you exactly how they connect a high-level, practical ML problem with the foundational mathematical choices you have to make when you're building a model. And the sources all agree that every machine learning system breaks down into three core components.
That's right. It doesn't matter if you're training a huge language model or just a simple predictor, you are always dealing with the same trinity: data, models, and learning.
Okay, so before we even jump into the math itself, let's talk strategy for a second.
Yeah.
If someone listening needs to get this math knowledge fast, the source material offers two really contrasting ways to tackle it.
Yes, the classic dilemma. First, you have the bottom-up strategy. This is what mathematicians love. You start with the absolute foundation sets, groups, fields, and you build up all that rigor slowly. The strength is, rock-solid understanding, but the weakness is motivation. As a practitioner, you often forget concept A before you even find out why you needed it for application Z.
And then there's the other way, the practical top-down approach.
Right. The top-down way is goal-driven. You start with a specific need. I have to build a classifier, and you just drill down to the bare minimum math required to make it work. It's super motivating because you always know why you're learning something. The risk, though, is that you build all this knowledge on what the sources call shaky foundations if you skip too many of the basics. We're going to try to get the best of both worlds today.
Okay, let's start with data, the first pillar. The foundational assumption in all of ML is that data has to be numerical. I mean, even if you start with an image, a sentence, a voice recording, it has to end up as numbers. And once it's numerical, we represent it as vectors.
And that word vector is just a fantastic example of how context completely changes meaning.
Okay, let's unpack that. If you come from a computer science background, what is a vector to you?
It's just an array of numbers, an ordered list. Like 25, 180, 75, maybe representing a customer's age, height, and score. It's a container.
But if you come from a physics background,
Then it's a geometric arrow. It's got a direction and a magnitude. You can actually plot it on a graph.
and then the most powerful abstract view, the mathematical one.
A vector is just an object that follows two simple rules. You can add it to another vector, and you can scale it. That's it. And that mathematical abstraction is what gives machine learning its power and its flexibility. It lets us treat everything from sound waves to, customer preferences as mathematically equivalent things we can manipulate.
So that's the data. Now we move to the model, the second component. If data is the input, the model is the engine. What's it actually trying to do?
A model is always a simplification. Always. It's a structure that tries to represent the real but, unknown process that generated your data in the first place. Think of it like a clean map that abstracts away the messy reality. A good model captures the most relevant parts and pulls out hidden patterns, which lets us make predictions about the real world without doing costly real-world experiments.
And finally, learning. The third piece. This is where we set the model's internal dials, its parameters, to find the best settings. We learned the process of optimization can be framed in one of two ways, right? The probabilistic view or the optimization view.
Yeah, but in either one, the goal is identical. Use numerical optimization methods to find parameters that make the model perform well on unseen data. If it only works well on the data it trained on, we've achieved nothing useful.
And these three components, data, model, learning, they're the foundation for what sources call the 4 pillars of machine learning. These are the big goals, the types of problems we solve: regression, dimensionality reduction, density estimation, and classification. We'll be tying the math back to these.
So since we've established our data lives as vectors, the math of how we relate those vectors to each other is, well, it's critical. This is where we get into analytic geometry and linear algebra.
Okay, so we had two customer vectors. Let's say customer A and customer B. How does the math figure out if they're similar?
We measure their similarity geometrically. The core idea is actually really simple. If two vectors point in roughly the same direction, we consider them similar. And if they're similar, they should probably have similar outcomes predicted for them. To make this formal, we use an inner product, which is usually the dot product.
Right, the dot product. It takes two vectors and just spits out a single number. And if that number is big and positive, the vectors are aligned, so the data points are similar. If it's near zero, they're orthogonal. They have almost nothing in common.
Exactly. Similarity is fundamentally a geometric calculation of distance or angle, and this measure lets us find neighbors, group data, define decision boundaries, all the stuff that's essential for classification and clustering.
Now, if we scale up from just comparing two vectors to analyzing a huge collection of them, we hit this idea of vector subspaces. Why is the idea of a closed set of vectors so important for ML?
Because it defines a constraint. A vector subspace is a smaller part of your bigger data space that's closed under our main operations, meaning if you add or scale any vectors that are already in that subspace, you're guaranteed to stay inside it. You never leave.
And that closure is what lets us do the key operation for simplifying data, orthogonal projection.
And this is where we link geometry directly to one of our pillars, dimensionality reduction. When we project, we take a data point from a really high dimensional space, and we find the closest possible vector to it that lives in a much lower dimensional subspace. This is the mathematical recipe for compression.
Okay, give us the intuition here. Why bother projecting in the first place?
We project because we believe that the signal, the really meaningful information in the data, it only occupies a small, specific slice of that whole dimensional space. The rest is just redundant noise. So, for example, if you have 100 features describing a car, maybe only 3 of them, like size, horsepower, and weight, are truly independent and necessary. Projection finds that 3-dimensional subspace that captures, say, 99% of the important information.
And the calculation for that projection. I've seen the formula. Let's say onto a single basis vector we'll call the dollar. It's often shown as lambda equals the inner product of x and b divided by the norm of b squared. That looks a little intimidating, but what is that lambda value actually telling us?
Right. It's not just some abstract formula. That value, lambda, it's a coefficient. It tells you exactly how much of your original vector, $6, is pointing in the direction of that important dimension dollars. It's the recipe for finding the coordinate in your new compressed space. This is the engine behind principal component analysis, which is our go-to for dimensionality reduction.
The problem, though, is that a single vector is just one data point. To deal with the complexity of millions of data points and hundreds of features, we have to scale up from vectors to matrices. Matrices represent these huge data tables and also, crucially, the linear transformations that turn inputs into outputs.
And when you're dealing with these massive data structures, you need tools to reveal their inherent structure. And that means decomposition, breaking a complex matrix down into simpler, easier to understand parts. And we often start by hearing about eigendecomposition.
Right. Eigendecomposition is great because it shows you the natural ways a matrix scales things. It factors a square matrix of many into another PDP one.
Yeah.
But there's a massive limitation for ML practitioners, isn't there?
Oh, absolutely. The main problem is that it only works on square matrices. And if your data set is rectangular, say 10,000 examples by 50 features, eigendecomposition is just. You can't use it. And 99% of real-world data sets are rectangular. So that forces us to move to a more universal tool.
Which is why the singular value decomposition, or SVD, is so incredibly important.
The SVD is rightly called the fundamental theorem of linear algebra for practitioners because it can be applied to all matrices, any shape, any size, and it always exists. It factors any matrix $800 into 3 pieces. 1i equals C sigma VT dou.
So we've got these 3 matrices, NERT, sigma, and VDALA. Can you help us visualize the intuition here? What are those matrices actually doing?
You can think of SVD as breaking down any complex linear transformation into 3 sequential steps. The first matrix, β to dollar, performs an initial rotation of your data. a basis change in the input space. The middle one, sigma, is the important one. It has the singular values on its diagonal, and it dictates the stretching or scaling of those dimensions. It can even change the dimensionality. And then finally, $$ performs a final rotation in the output space. So it's saying any complex data transformation is just a rotation, a stretch, and another rotation.
That is powerful. And the practical magic, it really comes to life in what's called low-rank matrix approximation, where we use a truncated SVD.
This is the workhorse application. If you have a huge high-rank matrix Euler, you can create a rank color approximation, we call it at k, by only using the first term and no singular values and their corresponding vectors. Since the singular values are sorted by size, we're guaranteed to keep only the most important dimensions, the ones that account for the most variance. We're prioritizing the signal.
Let's talk about that striking example from the source, image compression.
Right, so you take a large grayscale image, say a 1432 by 1910 matrix. That's over 2.7 million data points. If you apply a rank 5 approximation using only the 5 largest singular values, you're basically rebuilding that image using just 5 weighted simple matrices. You end up needing only about 16,700 numbers to store the image.
Wait, you're telling me we can save over 99% of the storage space and the image still looks essentially the same?
Yes, because the vast majority of those 2.7 million numbers in the original image matrix were just redundant. SVD found the 5 most important structural components that define that image, and it just discarded the rest. It's efficiency optimized by mathematical insight.
And SVD's power isn't just for compression. It's for finding hidden structure in abstract data too, like analyzing preferences.
Exactly. Consider the classic movie rating matrix. You have people rating different films. If you do a rank 1 approximation, you often find the single biggest common factor. Maybe it's a sci-fi action versus non-sci-fi theme. If that rank 1 approximation gives you bad predictions, you move to rank 2.
That's fascinating. So SVD is basically a statistical X-ray. It's telling us that maybe this data set only has 2 meaningful themes of preference and everything else is just noise that we can safely ignore.
Precisely. If a rank 2 approximation provides a really close fit to the original data, it tells us that adding a third factor or the third singular value contributes almost nothing meaningful. SVD gives you empirical evidence for the true complexity or the simplicity of the underlying structure.
Okay, so we've covered how to structure data as vectors and how to decompose and simplify these big matrices. Now we get to the final core concept, learning. How do we actively find the best parameters to make our models useful? This is the world of vector calculus and optimization.
Right. Training models is an optimization problem. We are searching for a parameter vector, we call it theta, that minimizes some kind of penalty function. We call that the objective or loss function. We're just trying to find the bottom of a mathematical valley.
So if we're standing somewhere in this landscape of possible solutions, what mathematically tells us how to get to the bottom of that hill? Is that where the gradient comes in?
That is exactly what the gradient is for. The gradient is a vector that tells you the direction of steepest ascent. It points directly uphill. So if we want to minimize the loss to slide downhill as fast as possible, we just move in the opposite direction, the direction of the negative gradient. That is the engine of gradient descent.
And in the simplest case, this leads to something called empirical risk minimization, or ERM. If we use the squared loss function, the difference between our prediction and the real value, squared, we're solving the least squares problem, which is the foundational approach for the regression pillar. We're just trying to minimize the loss on the examples we have. The formula is min over theta of 1 over n times the norm of y minus x theta squared.
But focusing only on minimizing that risk on the training data is the shortest path to the greatest pitfall in all of ML.
Overfitting.
Overfitting. It's that frustrating situation where the model has an exceptionally low training error. It knows the training data inside and out, but when you show it new unseen test data, it performs terribly. It has essentially memorized the noise instead of learning the signal.
So to fight this, we introduce regularization.
Exactly. Regularization forces a compromise. It biases our search away from those overly complex or extreme parameter solutions that might fit the training data perfectly, but just fail to generalize.
And the most famous example is $2 regularization, where we add a penalty based on the size of the parameters. We're minimizing the fit error and the complexity of our model at the same time. The new formula is the old one plus a lambda times the norm of theta squared.
And here is where you see this profound conceptual bridge that connects the optimization world and the probabilistic world. That Twilody-2 regularization term is mathematically equivalent to placing a negative log Gaussian prior on the parameters theta when you're using maximum a posteriori or MAP estimation.
Wow. So on one hand, we're just adding a simple penalty term to an equation. But on the other hand, the math confirms that what we're really doing is expressing a philosophical belief that simpler models with smaller parameters are just inherently more likely, more plausible. That's a powerful insight.
It connects regularization, geometry, and probability all in one seamless mathematical package. Finally, since the whole point of this entire exercise is to estimate performance on data we've never seen, we can never just trust our training error alone. We need a reliable way to check for that generalization error.
Which brings us back to cross-validation, k-fold cross-validation, where you have to partition the dataset k times and you cycle through which part is for training and which is for validation.
It is the necessary sanity check. It lets us approximate the expected generalization error honestly, so we can guard against the model fooling us into thinking it's performed well when it has just overfit. It can be an expensive process computationally, especially when k is large, but it's absolutely essential for any real-world deployment.
This has been a whirlwind tour through the required foundation. We've seen how linear algebra turns data into useful vectors and gives us similarity measures through the dot product. We saw how a universal tool, SVD, lets us simplify and compress massive data sets, finding that essential low-rank structure.
And we covered the essential engine of learning itself: optimization using the gradient, minimizing risk, and ensuring models can generalize by adding structure through regularization, which we now know is a probabilistic equivalent of placing a prior belief on simplicity.
So equipped with this modular foundational understanding, you really have the mathematical toolkit you need to approach those four pillars we started with: regression, dimensionality reduction, density estimation, and classification.
Yeah.
And to understand the math decisions that are driving each one.
That's right. The math is the map.
And as we close, let's circle all the way back to SVD for a moment. We saw how it can take a huge complex matrix and accurately represent it with a tiny subset of values, identifying the few core factors that drive the whole data set. And that raises an important question for you, the listener, to think about. If SVD can find the hidden simple structure underneath a complex image or data table, what other seemingly irreducible complexities in the world, in business strategy, in economic data, maybe even in biological systems, could actually be hiding a surprisingly simple, low-rank structure just waiting to be mathematically decomposed?
Food for thought indeed.
That's it for this deep dive. We'll see you next time.